let's continue. Particle and nuclear physics. So let's see here. This is a new chapter already, actually. It's a new chapter. It is still more or less similar topics. They are like the subparticles, subatomic particles, which talk about electrons, okay, alpha, gamma, beta, which is the thing inside the atoms also. So that's why we put, yeah. Oh, okay. So you learned this chapter already, lah, which means, okay. So then this will be your revision then. Okay. So let's see. We have alpha decay. So alpha decay, of course, that is the 4-2 helium nucleus. Helium nucleus. Okay. So 4-2 helium 2 plus. So this is alpha particles. So it's the helium that loses 2 electrons. So it becomes positively charged. So very desperate for electrons. So that's why this is under the radioactive substance. So the nuclear number decreases by 4. And then that means when you want to balance the equation, right? So make sure you minus 4 for the nuclear number, and then your proton number decreases by 2. Okay, so let's say for example, initially you have X, which is A and Z. So after that it becomes Y with alpha decay. So of course the nuclear number has to minus 4. The proton number you have to minus 2. So this is the example. Now we move on. The next one, beta minus decay. So beta minus decay is basically electrons. Okay, so this is electrons. 0 minus 1. Okay, so this 0 minus 1 means something also. That means the proton number seems like decreases by 1. What is meant by that? Actually, it is useful when you want to balance the equation. Let's say for example, if you have X, which is AZ, then it becomes W, let's say, plus beta minus, which is 0 minus 1. So if you see the number on top, this is A, this is 0, then here have to be A then. Have to be A. And if you see the number at the bottom, if left hand side is Z, then here's minus 1. So in order to get back Z, right, so it has to be Z plus 1. Z plus 1. So that's why the minus 1 has its significant here. So it means when this element X releases beta minus, so the protons number increases by 1, meaning that 1 protons is produced. Yeah, 1 proton is produced. So maybe you're wondering, like, how come the nuclear number does not change? Because what happened here is 1 neutron changes to 1 proton plus 1 beta minus. Yeah, logically this is true lah. As you know, neutron is having no charge. Proton is positively charged. So when you want to form something positive, then the negative charge you have to remove it. So the negative charge is the electrons. So that's why when you think of that and you try to count or imagine, so at the end you will realize there should have no change in nuclear number. So as there is decrease of 1 because of neutron. Then after that you plus 1 because of proton. So -1 and +1, then no change in nuclear number. But proton number increased by 1. Okay. Now, let's see the next one. Okay. This one, beta positive decay. Positron. Okay, positron. Huh? So it's 0 plus 1. Beta positive is similar to this. But it's the other way around. So it's positively charged. This -1, this is positive 1. Okay. Now, for example, let's say I have AZX. Change to WX. Yeah, it's a positively charged electron, so we call it positron. So this beta positive. So how to balance the equation? We use common sense. So the common sense is if you have positive 1 on the right, so in order to balance with the z on the left, so here has to be z minus 1. Z minus 1. And then this one, no change. Huh? As you can see here is 0. Here a plus 0 is a. Here also a. Okay, so what happened is one proton changes to one neutron plus one positron. Logically, this is kind of reasonable. Proton is positively charged, so they change it to neutron, which is neutral. So the positively charged is removed as positron. Okay. Then next one, gamma decay. Gamma decay, there is no number for the nucleon and the proton number. So this is just energy. So proton and nucleon number unchanged. So the equation is basically ZX with high energy. So releases the energy as gamma. Then this becomes low energy. So gamma ray is releases in that way without changing the proton and neutron nucleon number. Okay, so let's move on. 13.2, mass energy equivalence. So first we have Einstein mass energy relation. So E equal to mc square. E equal to mc square. So what happened here is they are trying to say that when radioactive decay happens, so there is mass defect happens, a mass defect. So mass defect is where the mass of the reactant, right, and the mass of the products are a little bit different. Okay, I mean the product has smaller mass, so mass defect happen. So that mass defect, right, is where the mass changes to energy. Okay, so mass changes to energy. Yeah? So that is what discovered by this scientist. And the relationship between the mass and the energy is you take the mass defect, multiply with the velocity of light, which is 3 times 10 to the power of 8, then you square it, and then you get the amount of energy that releases during the process. Yeah, speed of light. Okay, so it's written here. C is the velocity of, this one typo error, velocity of light in free space. Okay, so they said mass of a system increases when energy is supplied to it. So that means example, C is constant. C is 3 times 10 to the power 8. Okay, so let's see one example for this statement here. They say if you want to increase the mass of the system, you just supply energy, then the energy will change to mass. Okay, will change to mass. Okay, so example, voltage is supplied to a proton, then E equal to EV, electrical energy, equal to mc squared. So where E is the 1.6 times 10 to the power negative 19. Okay, so this is an example. So from this statement, right, we see something also. We see mass defect. This is the one that I mentioned just now, decrease in mass or mass excess. Okay, so this statement is about mass excess. So mass increase, mass excess. So mass excess is increase of mass because energy is supplied to it. Energy is supplied. So what I mentioned just now, mass defect, right? So mass decrease and energy is released. Yes. Now, okay, let's see the next point. Mass defect, change in mass, that means the difference between the total mass of the individual separate nucleons and the mass of the nucleus. Okay, so that is mass defect. So basically mass defect is the mass of the product minus the mass of the reactants, and then you get the mass defect. Okay, so let's see the next one. Binding energy. The minimum external energy required to separate all the neutrons and protons of a nucleus. So you try to imagine, neutrons and protons are hold together in the nucleus by some attraction inside the nucleus itself. So if you want to separate them, you need binding energy. So it is also the energy released when the nucleus is assembled from its constituent nucleons. So it also put it in the other way around. That means if you want to put the neutrons and protons together in the nucleus, and then energy is released. Okay. So energy is absorbed when you want to separate them, and energy is released when you want to assemble them. Okay. So that is binding energy. Okay, I give you one example for binding energy. Okay, example. Carbon 12. So first, mass of individual and separate nucleons. Okay, so we have to know that carbon 12 has 6 proton, 6 neutron, and 6 electrons. So let's say they are currently separated. So now you want to assemble it. So you have to put them together and form carbon. Okay, now let's do some calculation here. So first we find out their mass. Okay, so their mass is, if I add up 6 protons, 6 neutron, and 6 electron, so I will get 12.098934 atomic unit. Okay, so after that, we go and check the mass of the carbon 12 atom. So of course this is going to be 12U. Okay, so you realize that if you count the mass of individual protons, neutrons, and electrons, you get mass that is slightly greater than the mass of carbon 12 atom itself. Okay, so that means there is a delta M over there. So we minus these two, then you get 0.098934 U. Okay, so this is the delta M, and then you can use this to count the binding energy. So to count the binding energy, so we use E equal to mc squared. So the E we change it to delta E, the M I change it to delta M. So the delta M 0.098934 multiply with the atomic mass unit. Okay, the value is 1.66 times 10 to the power of negative 27, and then multiply with 3.0 times 10 to the power of 8 square. Okay, then let's say we count it out. Try to find out the binding energy. 1.48 times 10 to the power of negative 11 joule. Okay, so that means you want to put 6 protons, 6 neutrons, and 6 electrons together to form carbon 12 atoms. This amount of energy is released. And at the meantime, if you have one carbon 12, you want to break down the atoms into 6 protons, 6 neutrons, and 6 electrons, then this amount of energy is absorbed. So it means something like that. That is the idea of binding energy. Okay, so now let's move on. Okay. Yeah, this point. The binding energy of a nucleus is a measure of how tightly the nucleus is bound, and hence how stable it is. So of course there's a relation between the stability and binding energy. So of course if the binding energy is big, then it means it is stable. Okay, so example, or maybe we go through this point first. Binding energy per nucleon, so you take binding energy divided by the nucleon number. So of a nucleus is the ratio of the total binding energy to its nucleon number. Take binding energy divided by nucleon number. The higher the binding energy per nucleon, the most stable the atom is. So let's see example. Okay, this one, example. Oh, you're asking difference between nucleon and nucleus. Uh, nucleus is, nucleus is the region, the region in the middle of the atom. So that place is nucleus. Nucleon is more basically the thing inside the nucleus. So nucleon is like proton and neutron. Okay, so yeah, nucleon. Yes, nucleon is the general term to represent proton neutrons. Yeah. Okay. Now let's see example. So binding energy per nucleon, mega electron volt versus nucleon number. Okay, so the graph will be like this one. Okay, so the graph look like this. Okay, let's see some example here. The Of course the first one is hydrogen. Hydrogen take the lowest nuclear number. After hydrogen is helium. So helium is taking a very high binding energy, so that means it's very stable. And then after that you can see carbon, which is stable also, oxygen, which is also stable, and then one of the maximum value taken by all these is the iron. The iron has the greatest binding energy, so showing that it is very stable. Okay, so this is the example how it looks like. Another information is curve for mass defect per neutron. Mass defect per neutron is same graph with this one. Their shape looks the same. So whenever you see this graph, it has two possibilities. Either it is binding energy per nucleon or curve for mass defect per neutron. So they have the same graph. Okay, and then one more thing, calculation. Okay, I put one more example here. If you use 4.5 gigawatt is used, 4.5 gigawatt is used to accelerate a proton, then calculate the increase in mass. So this is to understand the statement given on top there. So where you have a statement saying that mass of a system increases when energy is supplied to it. Okay, so let's see the calculation. Okay, so we have to use something like this to do the calculation. Okay, so let's see how. So E equal to 4.5 gigawatt. Okay, so our question is 4.5 gigawatt. So, but when you want to count the energy, right, you have to use electron volt, okay, EV. Yeah? So you have to use 4.5. The idea is EV, energy equal to EV. So the energy involved here is the electron charge, or 1.6 times 10 to the power negative 19. The volt is 4.5 giga. So this is the amount of energy. So at the end you will get 7.2 times 10 to the power of negative 10 joule. So this is the energy involved. Then we use E equal to mc squared. Then m equal to c squared over m, c squared over E. Okay, then we substitute value 3.0 times 10 power 8 square. So E is 7.2 times 10 negative 10. Okay, so this is the energy. And when you divide them, so, oh no, the other way around. The other way around. Huh? So when you rearrange the equation, right, supposed to be m equal to E over c squared. So 7.2 times 10 negative 10 over over c squared. C squared is 3.0 times 10 power 8 squared. Then you get 8.0 times 10 to the power of negative 27 kg. Okay. So this is the mass, the mass of the protons. Okay. This is the increase in mass. When you look at this value, you don't feel anything. But if you look at the rest mass of a proton, which is 1.66 times 10 to the power negative 27, you can see it increases a lot. Imagine a proton had this value 1.66 times 10 to the power negative 27 kg. Okay, so now it increases like 5 times of the original value. That is a lot, So try to imagine that. Okay, it increases 5 times. So it happens to protons. A human being cannot. You want to increase 5 times, like very hard to happen, right? So it happens in protons. Okay, over here, atomic mass unit. This one should not be too hard. It is about U. So 1 U is defined as 1 over 12 of the mass of a neutral atom of carbon 12, approximately equal to 1.661 times 10 to the power negative 27 kg. So this is how heavy is 1 U. 1 U, this is the mass. And 1 U is 1 over 12 of the mass of carbon 12. Okay, so mass excess is equal to mass in U minus nucleon number. So you want to count the mass excess, then you can use this one. 1.661. This is for, if this value you times 12, then it will be the mass of carbon 12. Yeah, this is U. Yeah. This is 1 unit basically. Okay, now let's see the next topic. 13.4, nuclear fission and fusion. Okay, so what is fission? Process in which a massive nucleus splits to form two smaller fragments. So you can see here, fission. Okay, fission is here. Okay, one massive nucleus splits into two smaller fragments. So this is breaking down. The large nucleus has a lower binding energy per nucleon. Lower binding energy means not stable. Okay, so split into fission fragments which have higher binding energy per nucleon, and it becomes more stable. So they split because they are not stable basically. Okay, now fusion, process by which two very light nuclei, so as in here, two very light nuclei join together to form a heavier nucleus. These two join together form a heavier nucleus. Okay, two light nuclei fuse, so the final binding energy per nucleon will be greater than the original value. So again, no matter they combine or no matter they break down, they want to become more stable. So that's why when you see the graph, they are like always going up. You know, this is binding energy per nucleon, which represent the stability. So they are getting more stable for this case, and they are getting more stable for this case also. Okay, so in general, if energy is released in a nuclear reaction, then it shows that the binding energy of the product nuclei is greater than that of the reactants. Okay, so something like it is exothermic. It's exothermic. So exothermic is where it releases energy to the surrounding and then it becomes stable. Okay, so it becomes stable at the end. Okay, so you can see a few important conclusions here. The first important thing is when you look at these statements, you will know that binding energy per nucleon increase after fusion or fission, showing that they are getting more stable. And then this one also exothermic. They say exothermic energy released to the surrounding, so it becomes stable also. And in that case, binding energy will increase. Okay, so now let's see here. Okay, so let's look at 13.5 then. 13.5, spontaneous and random nature. Okay, so first, radioactive processes are random and spontaneous. Okay, so what is meant by random? That means impossible to predict, and that means impossible to predict when radioactive process happens, and each nucleus has the same probability of decaying per unit time. So we cannot predict when is the radioactive process happens. We also cannot predict which nucleus will undergo radioactive process. So we can't predict because it happens in random. And then spontaneous. Spontaneous is different from random. Spontaneous is not affected by external factors such as the presence of other nuclei, temperature, and pressure. So that means if you change the temperature of the system, the radioactive process still happens in the same speeds or in the same rate, so it's spontaneous. So if you change the pressure, the radioactive process still happen in the same rate also, so showing that that is spontaneous. Yep. Uh-huh. So that means you cannot predict. uh, okay, let's say I draw out a picture for the random. So let's say these are the radioactive substance, which is solid. Okay, so you have many atoms over there. So first we have groups of atoms here. We cannot predict when is radioactive decay or radioactive process happens. We cannot predict that. Okay. The second thing is, out of the groups of atoms here, we cannot predict which atoms is going to decay next. So we cannot predict two things here. Yeah, that is the idea of random. Yeah. Okay. Now, next one. Evidence on a graph. Okay. So first, for random, graph will have fluctuations in count rate. Okay. So example, this is the graph. You can see fluctuation happen like this, like shaking. Okay, shaking. Shaking, that is the proof of, or the evidence of random. You can see fluctuations. And then spontaneous. Graph has same shapes even at different temperature, pressure, and etc. So meaning that if you do it at two different temperature, their graph is still the same. Uh, yes, fluctuation is like that. Okay, so you will see something like this. Fluctuation is the shaking of the graph. Okay, spontaneous is like the red and the blue. Yeah, spontaneous. You change the temperature and the pressure, the graph still the same. Okay, now radioactive decay. Okay, so now we have some formula together with some calculation here. So first, let's say the rates of decay of a given nuclide at any time is proportional to the number n of nuclei present at that time. Okay, so meaning that if you have more, if you have more n, if you have more, then you see there's a negative here. Okay, so if this is big, then this is small. Okay, so I write it down first in this way. So dn over dt is proportional to negative n based on the statement there. So meaning that the decrease in the decrease of nuclei means greater rate of decay. So it means something like that. Yeah, inversely. As you can see, when this is negative, then this is increasing. When this go down, this one will go up. Yeah. Then after that, you can see lambda come in. So lambda is known as decay constant. Okay, decay constant. Then after that, we have the next point. The activity A of a radioactive sample is the rate at which nuclei decay or disintegrate. Okay, so activity is detected by using the GM detector. Okay, it's a machine instrument, so you can use it to detect the activity. And then what they're trying to say here is they say A is equal to negative dn over dt. Okay, so if you see the first equation here, over dt is equal to negative lambda n. Negative lambda n, meaning that dn over dt is a negative value. Okay, it's a negative value. So imagine when this is a negative value, together with another negative sign in front, so at the end the activity is a positive value. Okay, it's a positive value. So activity is a positive value. That is one thing. The other thing is decaying rate, if it's more negative, that means A is more positive. So it means something like that. That means if they decay very, very fast, and then activity is very big. Okay. Then next one, the decay constant, lambda, is the probability that an individual nucleus will decay per unit time interval. So lambda. Okay. So lambda means the probability of the individual to decay. And then after that, A equal to lambda n. A equal to lambda n. So you see this is negative lambda n. And then imagine you substitute negative lambda n over here. And then you get positive lambda n. So that is the activity. A equal to positive lambda n. So this is a positive value. This is a negative value. Showing that this will decrease, as you can see, decrease. Okay. Then the above relationship can also be written as x equal to x naught e to the power of minus lambda t. So this is the formula to represent the graph. You know, the graph that goes down in this way is basically an exponential graph with negative power. So this is the equation to represent that. Okay, so where x could represent activity. So x can be, you can change it to a, so they are trying to say that you can change it to a. So you can change it to a equal to a naught b minus lambda t. I can change it to a. Or you can also change it to number of undecayed nuclei. Yeah, n. N and n naught. Okay. Then you can also change it to receive count. So you have three options. Receive count is not lambda. Receive count, let's say, I don't know what symbol they use. Let's say receive count. Let's say I just call it RC, receive count. So that means that formula, right? You can change it to n equal to n naught e minus lambda t, or receive count equal to original receive count e to the power of minus lambda t. Okay, so we have many options to replace the x and the x naught. receive count, imagine you are using the Gauger-Muller counter, which is a machine to count the radioactivity. They will count how many pulse rate per unit time. So then they will present the graph as receive count, like this, something like this graph. Receive count per unit time, something like this graph. But the y-axis is not activity anymore. It is receive count per unit time. Receive count versus time. Then the graph will be like that. Or if you use number of undecayed nuclei versus time, the graph is also like that. Okay, so okay, a bit more, yeah. Sorry. Unit for activity. Um, oh, BQ. 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 Okay, so I write for you the unit of activity, which is here. BQ, which is back-quarrel. Back-quarrel. If you want to talk about the unit, one more unit to know about. The unit for lambda is per second. Per second. Yeah. Now, let's play around with the formula to see how is all this works. Okay, so I will start from dn dt equal to minus lambda n. So we need to use mathematics. Sometimes they ask you to derive. Okay, so after that, if I rearrange this, lambda is equal to negative dn over dt divided by n. Divided by n. If I rearrange it logically, it looks like this. Okay, then after that, lambda equal to, I purposely rearrange in a special way, which is like this. Negative dn over n dt. Okay, then you understand that this is the change in n over n. So this is the probability of nucleus decay. This one is per unit time. So that's why the lambda has that meaning. Okay, has that meaning. So as you can see over here, lambda is the probability that an individual nuclei will decay per unit time interval. So I arrange the equation, then you can see that. So beside this, we have another things to know. Dn dt equal to minus lambda n. We can do differential equation also. So where we can do 1 over n dn equal to minus lambda dt. Then we integrate on both sides. So ln n minus lambda t plus c. So we change the ln to exponent. Minus lambda t is c. Yeah. Yes, but not very popular. Okay, so then you will get EC E minus lambda t. So when t equal to 0, n is equal to EC. So n is equal to EC. So because of this, we get n equal to n naught E minus lambda t. So we get this, where N naught is the e to the power of c just now lah. So in general, it is x equal to x naught e to the power of minus lambda t. So you can see how we change the rate to the equation that they gave here, which is this equation. So you know how to change already. Separate the variable and integrate. Okay, so here, the activity of a radioactive substance represents an exponential decay. So that means the graph is exponential decay. That means the graph is like going down. Okay, the half-life of a radioactive is the mean time taken for half of the active nuclei in a sample to decay. So that means, okay, let's say this is activity versus time. So this is A naught. Half of the A naught is here. So this time is half-life. That is half-life. Okay, so half-life is where the activity decreases to half the time span. So assuming the initial activity is 1, so if this is 1, then half will be 0.5. Okay, so at half-life, the activity would be 0.5. So we use the formula just now. X equal to x naught e minus lambda t. So if this is 1, then this is half. So we just use some number to represent the relation between the initial and the half-life. So 1 and half. Then you simplify it. You ln both sides. Then you get this. Then you bring the t half down. Then you get this formula. So we use this formula to count the decay constant. So decay constant, use this formula. So you also need to know how you get this formula also. So at the end, there are 3 deriving process that you need to know. So how you use the dn over dt to get the lambda as probability per unit time. That's the first one. The second one is how you use dn over dt to get the equation over here, this equation. This is the second one. And the third one is how you use this equation, substitute value and get this formula. So this formula is to get the decay constant. Okay, so finish up for this chapter.
Phosphorus 30 was the first artificial radioactive nuclide to be produced in a laboratory. This was achieved by bombarding aluminium-27 with alpha particles. A partial nuclear equations to represent this reaction is, so you can see the equation, aluminium plus alpha, then you get phosphorus and phi. Okay, so when you look at this equation, first we need to know that the alpha here is actually the helium. So helium is 42. So because of that, when we write the answer here, for the first one, the alpha particle, we write 42 helium. So if this is 42 helium, then we look at the nucleon number, 27 plus 4, which is 31. But on the right hand side, we have 30, and you should expect this should be 1. And after that, we look at the proton number. This is 13 plus 2, which is 15. And this is 15 on the right already. So we should expect this to be 0. Okay, so if it is 1, 0, then you should think of this as neutron. Okay, as neutron. So the phi over there is neutron. Now let's look at part B. Data for the rest masses of the particles in the reactions are given in figure 14.1. So you can see the mass over here. Calculate for this reaction the change in the total rest mass of the particles. So change of the mass. So basically what we need to do is we need to find out the total masses of the reactants, and then we find out the total masses of the product, and then we have to take the heavier one minus the lighter one. Okay, so let's say I find out the reactant first. Okay, the reactant first. So we have 27 aluminium and alpha. So I have to add up this and this. So for the mass of the reactant, we have 26.98153 plus 4.00260. Okay, so we use calculator to add up these two. 26.98153 plus 4.00260. So this is in terms of U. So it is 30.98413 U. So these are the total mass of the reactants. The mass of the products, we have phosphorus 30, which is 29.97830, plus the phi, which is the neutron in terms of U. Okay, so we add this up. So we have 30.98697 U. So from here we realize that the product is heavier. It's heavier than the reactants. So the mass change, delta M, is equal to, we take the heavier one, the product, minus with the reactant. Okay, so by subtracting this, we will get 2.84 times 10 minus 3 U. Okay, so this is the answer that you are going to put there. Okay, now let's move on. Part 2, the energy in Joule equivalent to the mass change calculated in part 1. So we use the Einstein equation. Change of energy is equal to change of mass times c squared. So the change of mass just now is 2.88 times 10 to the power of negative 3 U. And the U is 1.66 times 10 times 10 to the power of negative 27. And the speed of light is 3.0 times 10 to the power of 8. And you square it. Then you get the energy in Joule, 4.24 times 10 to the power of negative 13 Joule. Okay, so this is the energy in Joule. And now let's move on with part C. With reference to your answer in B1, comment the energy of the alpha particle such that the reaction can take place. So first of all, when we look at these questions, we have to know that there is an increase of mass in the system, as you can see here, from this value to this value, meaning that there is an increase of mass. in the system. So from the note, we also know that when there is an increase of the system, on page 4 we have this theory, mass of a system increases when energy is supplied to it. Okay, so we have this concept here, and we already count out the energies here. So this is the energy that you need to supply to the system so that the mass increases here. So we have to supply energy to the alpha particles. We have to supply this amount of energy to the alpha particles so that the reactions take place. So now, in order to write down the answer, first we can write the first point. Reaction causes net increase in rest mass of the system. Second point, alpha particle must have at least this amount of kinetic energy. Okay, so finish.